Hello everyone, my name is Juhyuk. This class is High Performance Concrete Engineering, and I'm in the Department of Civil and Environmental Engineering, Seoul National University. So this class today is the first lecture, so I will have an introduction of this class. So basically the objective and rubrics of this course, and also what is the most important concepts that I want you to remember at this first lecture will be explained. So a purpose of this class is to first of all introduce the concrete materials and also how to design the material level properties, because starting from that, we can upscale the material property to the structural level. But you will see later, concrete is very complicated material. So depending how we design the material at the material level, you will see lots of properties that we can actually modify. Okay? So shortly, purpose of this class is to provide a fundamental understanding on the manufacture technology and preparation method of these concrete materials, and also especially focusing on the high performance concrete material. So high performance concrete, the definition of the high performance concrete, high strength concrete, or ultra high performance concrete, all these similar but a little bit different definition of the concrete materials will be introduced today. And subsequently, you will have a chance to learn about cement chemistry and concrete chemistry, and manufacturing technology and material characterization, and the relevant design code for general concrete as well as high performance concrete. Okay. So as a grading rubric, you will have 4 or 5 homework assignment, and also we will have 2 exams. So midterm and final exam. And especially this lecture is designed for graduate students who do not have much background on concrete material. So if you don't have experience or if you don't have much knowledge on concrete materials, you will be okay to follow up this class. So evaluation method, attendance 10%, and homework assignment 4 to 5 homework assignment will be 20%, and we will have a midterm 30%, and final exam is 40%. So as a course introduction, I'm providing graduate level courses of this high performance concrete engineering class, and also advanced construction materials class, which is typically delivered in the first spring semester. So what is the difference of these two graduate level classes? So this class, high performance concrete engineering, basic knowledge on cement chemistry will be given, and how to produce the concrete materials. We have to mix aggregate and water and cement and also other admixtures together. So all these material properties of each ingredient of the concrete materials will be covered. And also mixed design for typical strengths of concrete material, and the mixed design for high performance concrete material, and ultra high performance concrete, and also the ultra high performance fiber reinforced cementitious composite or fiber reinforced concrete will be covered, and also time dependent behavior will be the last topic of this class. So let me tell you first why the concrete is so much complicated and so difficult to predict its material properties. Okay. Let's see, this is very typical the most important material properties of concrete material is the strength, right? Concrete strength. Okay, so I want to build bridges or I want to build apartment, then we have to design we have to satisfy the strengths of the concrete materials. Then what kind of procedures that we have to follow, what kind of mixed proportion, what is the requirement for each ingredient of concrete materials. We have to decide, right? So that can be the cement and water, the fine aggregate, and coarse aggregate. Okay, so cement and water, among these 4 ingredients for concrete materials, only the reacting component is the cement. There's no chemical reaction between fine aggregate and water or fine aggregate with cement. Okay, only these 2. They have some kind of a chemical reaction. Okay? These are inert component. Okay? So then this is the basic ingredient of concrete materials, and you will see in this class later. And then these components are getting more and more complicated because of many issues that I will explain later. Okay, so let's see. We have to determine the strength of concrete FC prime. This is the compressive strength of the concrete materials at certain date. It can be 28 days or it can be 7 days. Right? But these are all the variables. These will affect the concrete strength. If you test different shape of specimen, then the strength will be different. Okay? If you test cube specimen, cylinder specimen, okay, the strength will be different. Okay? Now, that is a natural phenomena of the concrete materials. If you apply the fast loading or slow loading, or different loading condition, then the concrete strength, as a result of the measurement, the strength will be different. That's also the natural phenomena of the concrete strength. And also, the matrix, if you see the matrix porosity, that means the matrix means as a result of the chemical reaction between the cement and water, it will be cement hydrate. Cement hydrate. Okay. So that is we call the matrix. Okay. So matrix porosity is also affect the concrete strength. Then what kind of a variable will determine the matrix porosity? Water to cement ratio, mineral admixture, degree of hydration, curing time and temperature, humidity, air content, all these parameters will affect the matrix porosity, and this will affect the properties of the cement hydrate. Okay? Even more difficult factor is transition zone porosity here. Okay? There's even more variables to affect the transition zone porosity of the cement hydrate. So let me draw a schematic diagram of concrete materials. So this is the volume of concrete materials, and we have coarse aggregate. This is coarse aggregate, okay? Then the remaining volume is supposed to be filled with This is fine aggregate. Okay. So typical size of the coarse aggregate is 25 millimeter. So you can get a sense of the scale of this material. And fine aggregate is less than a few millimeter, right? Few millimeter to 2 to 3 millimeter. Okay. So this is the scale of the concrete materials. So we call the remaining like a volume of these as a cement paste. And cement paste is a result of hydration. And hydration means the water-induced chemical reaction. So hydration means water and the cement. Okay, so as a result of the water and the chemical reaction between the water and the cement, we have a hydration product, and that is the cement paste. Okay, and even in this small cement paste, so there's no fine aggregate or sand here. And even for this cement paste, we have at least even in this small area, we have at least CSH, I'll explain this later, and Portlandite. And other AFM and AFT phase, depending on the curing environment and the hydration process. So we call all these as a cement paste. Okay. So as you can see, it has a multiple hierarchy of the substructure, and this is the reason why the prediction of the material properties or material performance of concrete material is so much complicated and almost impossible. And what is even more difficult is there is a pore. This is a pore structure. And this pore structure can be, the size of the pores can be large or it can be small. And the range of this pore structure is actually millimeter to nanometer size. Okay, so there's even the capillary size of the pore, nanometer size of the pore structure in the cement paste, and even in some space within this crystal of calcium silicate hydrate. This is calcium silicate hydrate. But anyway, all this is very complicated, intermixed or interrelated each other. So that is the reason why we have so many different parameters that we have to consider to predict or to even understand the material properties of the concrete materials. Then, among all these parameters, what is the most determinant parameter which will decide the strength of the concrete materials at the most? That is the property of this region. Okay? So what I'm saying is there are so many different variables. As you can see in the PowerPoint slide, there are so many variables that we have to understand the material properties of these composite materials. But among all of these lists, what is the most dominant factor to affect the material properties of concrete materials is the property of this region. Okay? This region is called the transition zone. Transition zone. Okay. So this transition zone is actually the space or the region between the cement paste and the coarse aggregate. Okay. So that transition zone parameters we can see is here. Okay. So transition zone porosity is the most dominant factor to determine the material properties of this composite material of concrete. So why? I will explain later. So actually, because of all this complexity, we can see it is almost impossible to precisely predict the material properties of the concrete materials, even for concrete strength. Okay? So because we have to know the strengths, right? Then we have to do the structural analysis and structural design, right? Then we can actually do the construction. But as you can see here, it is it's very, very difficult. So what is being doing in the field, we have to measure the actual strength of concrete materials from the same mixed proportion. Then we can eliminate all these factors, right? We can only control the specimen size and the loading condition. Then we can assume the strength of concrete material in this wall, for example, is the same that the strength of the actual specimen that we tested it. Okay, so anyway, in one line, concrete material is very heterogeneous and very complicated material. So this is the reason why we have to learn about the concrete and concrete structure in a graduate level, or even for the undergraduate, at the undergraduate level class, or even for graduate class, like you guys. This is the cement factory, modern cement factory. As you can see here, we start to burn limestone. Limestone is CaCO3. We start to burn this limestone at very, very high temperature. Okay, so this is the temperature, and at early ages, for example, so the age of ordinary Portland cement, we call it OPC, it's been already 200 years. Okay, so if you can imagine the situation at 200 years ago, at that time, it was very difficult to burn this limestone at very high temperature because they were not trying to burn a small quantity. They are trying to burn a huge quantity of limestone materials, right? So there was definitely a technical challenge to burn the huge quantity of the limestone at a very, very high temperature. So at that time, for example, 200 years ago, the firing temperature was not very high, so the cement quality is very low. But nowadays, we can use this kind of technical system to burn limestone at very high temperature with a great quality control and a huge quantity, so it will be increased significantly. Okay. So at that time, it can be less than, for example, it can be less than 600 degrees Celsius. But nowadays, it is more than 14 and 50 degrees Celsius. So as a result of this higher firing temperature to burn limestone is a raw material for cement, we was able to increase the quality of the OPC. And as a result of the increase of the quality of the OPC, we can increase the compressive strength, and also we can increase other properties as well. Long-term performance and tensile capacity, Young's modulus, all these kind of mechanical properties was increased by increasing the firing temperature of the limestone. Okay. So this is the brief history of the cement material. So let's take a look at the formulation of the modern cement, OPC. So we have to mix clay and limestone together, and we have to burn that kind of a mixture at a very high temperature, such as 1450 degrees Celsius, okay, in a large, very huge quantity. So we can imagine this is very difficult to uniformly burn the huge quantity of the materials. So this is definitely a technical challenge, because some regions temperature supposed to be higher than this 1450, and some region was inevitably temperatures should be lower than 1450 degrees Celsius. So anyway, we have to heat this kind of mixture, clay and limestone, at very high temperature, and we can gain this kind of material. These are called phases. So mainly we can get 4 main phases, okay? 4 main phases. So limestone will be decomposed, because limstone's chemical formula is CaCO3 will decompose into CaO and CO2. The CO2 will be released, right? And the clay, mostly the oxide composition is silica, alumina, and ferrite. So this one is silica, alumina, ferrite. So Si means silicon, right? SiO2 indicates silica, Al means aluminum, and the Al2O3 means alumina, and Fe is iron, and Fe2O3 is ferrite. So they are all decomposed at this very high temperature, and they have a chemical reaction between these two. Okay, so it will produce the CaO, SiO2 if they bind together, and 3 CaO, SiO2, and 2 CaO, SiO2, and 3 CaO, Al2O3, and 4 CaO, Al2O3, and Fe2O3. So you will see these 4 phases. These are the main components in the OPC. Okay, so OPC, ordinary Portland cement, is not a single material. This is a mixture of these 4 phases. Then what is the mix ratio of these 4 phases? You will learn the next lecture about the impact of the changing the weight ratio of all these 4 phases, because they have a different, obviously these 4 phases, they will have a different chemical reactions. It will impact the properties of composite materials in a different way. But the CO2 here from the limestone, CO2 will be released. Okay, so the problem of the OPC, ordinary Portland cement, is the CO2 emission. Okay, for example, if you can calculate the 1 ton of manufacture of the Portland clinker releases 1 ton of CO2 into the atmosphere. Okay, this is a huge problem nowadays. But people actually don't know much about this issue. We are aware of the CO2 emission from the car, right? So nowadays, globally, they are making more electric car or hydrogen-based cars, right? or hybrid version to reduce the CO2 emission from the transportation. But from construction sector, this 1 ton of cement is a sizable volume of the cement that we can imagine, right? But 1 ton of CO2 is a gas phase. Gas weight of 1 ton of CO2 is something that we cannot easily imagine, right? This is huge quantity of CO2 that is being released even at this moment, globally. And because of this huge quantity of the CO2 emission, the cement production, globally, cement production is responsible for 5 to 8% of the global CO2 emission. This is the largest number of contribution to the global CO2 emission, even much higher than the transportation and the other industries. So this is the largest number, okay? Largest number. But the reason why people don't know much about this issue is because we don't have many other options to replace this OPC with other so-called green cement or green concrete. So I will tell you more about this issue later. So let's take a look at about the result of the chemical reaction. Okay. First, this is the graph of CSH formation from the chemical reaction of C3S and C2S, right? And as a result, we also have CH formation from C3S and C2S, right? And then different color here. This is ettringite formation from the chemical reaction between C3A, gypsum, and water. Then this is going to be monosulfate. And as the hydration process goes on, the porosity will be decreased. This is porosity. So typically this is 30 minutes, and this is typically 6 hours. And after 1 day, we can get this monosulfate formation. So basically, the cement hydration process is the water consumption process. We have a designated volume, and there's a chemical reaction goes on, and then all the liquid phases will transform into the solid, right? So basically, there is a reduction of the pore. Pore means a void, and at the beginning, we call the volume of the liquid water. Volume of the water is treated as a pore. Okay? So technically, the porosity is the volume of empty region as well as the volume filled with water. Okay? So volume of empty and volume of water. Okay? And because the chemical reaction of the OPC is a water consumption process, the porosity should be decreased as hydration progresses. So if you think about this monosulfate formation, if the C3A is not enough, then at some point here, there's a decrease of the ettringite phase, but there's an increase of the monosulfate. So this is the case of this case. If sulfate is consumed before C3A has completely hydrated, this additional hydration goes on to produce monosulfate from ettringite. So this is the point. This is the reason why we have to see this kind of a monosulfate for monosulfate production and the reduction of the ettringite crystal. So this black means the calcium silicate hydrate, and this is calcium hydroxide, and this needle shape is ettringite crystal, and eventually all of this water-filled region will be filled with crystals, right? And the calcium silicate hydrate, if you see this phase, for example, this one, there's a calcium silicate hydrate formation at surrounding part of the cement particles, because cement will react with water, right? So this is unreacted cement, and this is the newly formed hydrated phases. So this is the CSH, and this is still OPC, because surrounded part is much more exposed to the water. So this is likely to react with water easily, but inner part of the OPC, they have to contact with the water to form hydration product, but water here should be goes through the hydration product to be react with water. Okay, so eventually all of this OPC will be reacted. So let's say this is the one cement particles, and this is a combination of C3S, C2S, C3A, and C4AF, obviously, and also gypsum. Right? They are mixed together. This is a cement particle. This is one cement particle, and all these are water, right? So they are surrounded. This cement particle is surrounded by water. So there is a formation of this calcium silicate hydrate. This is also kind of needle shape. And this calcium silicate hydrate, this is calcium silicate hydrate, and this is dense phase, dense. Okay. Because it has a strength, right? The reason why the concrete has some strength, because calcium silicate hydrate is the main contributor to the strength of this composite material. So there's a reduction of the cement particle, because this part has been react with water to form CSH, right? So still it has a cement part here. This is unreacted cement. Unreacted, still intact, unreacted part. But for further hydration or subsequent hydration, the water should goes into the CSH to be hydrated more, right? So at the beginning, the cement hydration can be very fast, because more particles are available for the reaction, because there's abundance of the water around the surface, right? Surface of the cement particle. But at some point, when this particle is surrounded by hydration product of calcium silicate hydrate, next hydration or additional hydration or subsequent hydration is not very easily be done. For example, now at this point, So at the beginning, hydration can be very fast, but at some point, when cement particle is surrounded by calcium silicate hydrate, the further hydration is supposed to be dependent on the diffusion. That means how fast this water can be, or how easily this water can penetrate into or through this calcium silicate hydrate to meet this unreacted cement. Then, if they can penetrate this CSH, there will be more hydration. There will be more hydration. And there will be more formation of this calcium silicate hydrate. So eventually, this water region will be filled with a hydration product. So that is the reason why at the beginning, the speed of hydration is very fast. But at some point, the hydration process is slowed down because at that point, from that point, the hydration is governed by the diffusion. That means water should penetrate into the calcium silicate hydrate to form additional hydration product, and then additional hydration product also has to expand to pull out this calcium silicate hydrate to occupy this original volume. Anyway, this is not like a single chemical reaction process. This is very complicated reaction processes. And then at some point, it has some strengths. That setting can occur. So that means it has some strengths. But this is not enough to satisfy the strength requirement. And after the setting, now we call it hardening. Okay? So setting, we have a region here. So for example, the setting is important. For example, we have to, let's say we cast concrete to fill the foundation. Okay? The next we have to put more concrete to fill that void. But this next casting process should be done before the final setting time of the first cast set. Okay? So setting is the initial set time, and also the final set time. So next casting process should be done within the final set, before the final setting time of the pre-existing concrete. So the standard ASTM standard or Korean standard or European standard, they are proposing how to measure the setting time. So setting is something between the true solid and the liquid, you can imagine, okay? And why we have this kind of set behavior? Because basically this is a liquid to solid transition, and then that transition is due to the formation of the calcium silicate hydrate and also ettringite crystal. So calcium silicate hydrate and ettringite, these are the dominant phases for concrete to have some strength. But from volume perspective, this calcium silicate hydrate will occupy much of the volume, 60 to 70% of the volume, 60 to 70% of the volume of the given system. Not only we have a calcium silicate hydrate and different mixture of crystal structure in the given volume, we also have a pores. Pores are everywhere in the concrete. Okay? In between this calcium silicate hydrate sheet, there's an interparticle pore spacing. This is pore, empty region. And there's a capillary void. And also there's entrained air bubbles for special purpose and entrapped air void. And if you can see the scale here, this is nanometer scale. This is micrometer scale. And this is millimeter scale, right? So the crystal structures are complicatedly intermixed together in a given volume, but also the pores. Pores are everywhere with different scales. So all of these make concrete application or concrete study complicated. Okay, so pore has an intermixed pore network. So interlayer water in the calcium silicate hydrate, and there's also the physically adsorbed water on the surface of the calcium silicate hydrate, and there's also the void filled with water in the capillary pore. So, like I mentioned before, we treat the water volume as a pore. Okay, so pore can be empty, but also the pore can be filled with water. And we treat both of them as a pore. So the crystal structure solid, also the pore network. This is also the solid network. And this schematic diagram indicates why the transition zone is important. And you can read about this part. And also the reason is we have aggregate here. This is non-reacting part. This is intact, and cement will hydrate volume except this aggregate, right? So they have a different bulk cement paste, but few, such as 30 to 40 micrometer or 100 micrometer region surrounding the coarse aggregate, we call that as an interfacial transition zone, ITZ, because this will determine the strength of this composite, overall material. Because this I strength, such as FC prime of ITZ, is smaller than FC prime of coarse aggregate. And if the FC prime of cement paste, then this ITZ strength will determine the strength of the composite materials, right? This is true for normal strength concrete, but for high strength concrete, strength is high, and we can make this ITZ strength stronger. Okay, then this equation is not valid anymore for high strength concrete, so they have a different mechanism to have high strength concrete, high strength. So anyway, so why we have the weakest link surround the coarse aggregate because of the ITZ. Then why ITZ has weaker strength? Because we can see the size of crystals at that transition zone. Okay, so in this transition zone, the size of crystal is large. Size is large, and pores also large. So basically there's more like a room or more space for hydration reaction at that specific region. Okay, and there's a less formation of the calcium silicate hydrate. So if you can compare this part, interfacial transition zone, and also this bulk cement paste, we can see there's more formation of calcium silicate hydrate in this region. There's more just calcium silicate hydrate, right? And then there's less volume of this calcium silicate hydrate here. Then the question at this point can be why there's a less volume of the calcium silicate hydrate in this transition zone, right? You will learn later why we have more space, we have a larger crystal at that transition zone, we have a less volume of calcium silicate hydrate. You will learn later, but the short answer to that question is because water to cement ratio at that specific zone is high than the water to cement ratio at the other part. Okay, so that means aggregate contains water itself, or it can absorb water, mixing water first. Before that water reacts with cement, it will absorb water very, very fast. So locally, it has higher water to cement ratio characteristics. Okay, so that means it has higher volume of the water. Okay, so that means there's more space, more pore, because pore now is the volume of empty region, and pore filled with water. Both are considered as a pore. So there's more space. Subsequently, they have more porosity, higher porosity, and there's a less amount of cement because water to cement ratio is high. Okay, so there's more cement, there's less cement, there's more water, and there's a less amount of cement. So as a result, there's a less amount of calcium silicate hydrate formation. So you can see, you will learn later about this mechanism in great detail. All of these belongs to the classification of the pozzolanic reaction. So what is the main primary reaction of this pozzolanic material? In the pozzolanic material, the amorphous silica, okay, amorphous silica in class C or class F or silica film, this amorphous silica is the only reacting part so far, and it will react with calcium hydroxide. This is calcium hydroxide and water and produce calcium silicate hydrate. So please try to remember this kind of chemical reaction, because this SiO2 from pozzolanic material, SCM, and the CaOH2, if you recall, the origin of the CaOH2 is coming from the hydration reaction. C3S plus water will produce CSH plus CH, right? C2S plus water will also produce CSH plus calcium hydroxide. So this calcium hydroxide, you will see later, this has a very, very important component from the chemistry perspective. So, like we learned previously, this calcium silicate hydrate, this is the most important component in terms of strength. So without calcium silicate hydrate, it does not have binding property, binding sand or binding gravel to have some strength from the composite material. So having more calcium silicate hydrate, we can expect it has a higher strength. Then what is the role of this calcium hydroxide here? So calcium hydroxide crystal will, part of this calcium hydroxide produced from the cement hydration will dissolve in the water. Okay, so this is water, and this crystal, some will stay, some will be stabilized as a crystal, but some will be dissolved in the water because we put water at the beginning. This is, water is a primary ingredient for making concrete. So it will decompose into Ca2++, 2OH-, right? So this is this is very important. So we learn in the pore structure, we have actually the water fill in pore, right? So this is concrete, it has pore, right? And it has micro scale or millimeter scale or sub-micro scale, different scales of pores in the concrete. But for small concrete, less than 100 micrometer, for example, these pores are actually filled with water. And also in the calcium silicate hydrate also contains the water between the interlayer, right? So you can expect, although we cannot see the water directly, we can expect a lot of things we can explain about the concrete by knowing that the concrete contains water inside. So if we can extract this kind of water, the pH of this water is very, very high, 12.5. So this means this pore solution, that is, the solution is a liquid, right? Liquid filled in the pore is highly alkaline solution. Even this is very toxic level, 12.5, because neutral is 7, right? So pore solution is actually the highly alkaline solution, and the reason why the pore solution has this high alkalinity is because the dissolution, partial dissolution of this calcium hydroxide in the water, and it will increase the pH, because pH is the concentration of the hydroxide ions. Hydroxide is OH minus, this is hydroxide. So because of the dissolution of calcium hydroxide in the water, it has high pH. Okay? So this calcium hydroxide can come from the pore solution in the pores of concrete. So it is very interesting phenomena that this amorphous silica in fly ash or in silica fume, it will react with this calcium ion and OH minus hydroxide and water to produce this calcium silicate hydrate. So actually, if you can recall the Roman concrete, chemistry reaction, this is the equation to explain the Roman concrete hydration. So they use the pozzolanic-based volcanic ash as an amorphous silica source, and also they use the quick lime as the calcium hydroxide source. Okay. So this is a Roman concrete recipe, right? But in the modern OPC recipe, we did not directly use the calcium hydroxide. That calcium hydroxide comes from the regular cement hydration here. So anyway, the main difference between this pozzolanic reaction and cementitious reaction is the speed of this reaction. The cement hydration reaction is very fast compared to the speed of this pozzolanic reaction. So this is very slow reaction. And as you can see here, the final hydration product is similar, calcium silicate hydrate. So basically, due to the fact that this pozzolanic reaction is very slow, so it can reduce early heat evolution and it can reduce early strength, but not long-term stress. So basically, we can enhance the long-term strength. And more important properties of this supplementary cementitious material based on pozzolanic reaction is we can reduce the porosity and permeability, so we can increase durability. This is the long-term performance of the concrete material. So you may expect why we can reduce this porosity. So basically, reduction of porosity will be related to the long-term strength development, and the reduction of porosity will be related to the reduction of the permeability. Permeability is the degree of the water penetration in the concrete, because concrete is not a closed form pores in concrete. It has all the pores are complicatedly or intermixed together. So as time goes on, the water will penetrate through the concrete specimen. So that is the definition of the permeability. So permeability can be reduced. So that means we can enhance the long-term performance. Okay. Then the main question here, how can we achieve the reduction of the porosity? So for the pozzolanic reaction, the main question here can be how can we reduce the porosity? Because in the cement chemistry notation, we can expect that this is the silica, and this is calcium hydroxide, and this is water, right? To form the calcium silicate hydrate, which is similar to the hydration product from the OPC hydration. I mentioned similar because is it equal, the CSH from the OPC hydration? OPC hydration. So is this equal or not equal, right? So this is a question, but how can we determine this equality? Because we still don't know the exact molecular structure of the calcium silicate hydrate. So something is unknown here. This structure, atomic structure or molecular structure is unknown still. So atomistically, molecular structure perspective, we still don't know the exact structure of the calcium silicate hydrate. Then how can we know this is equal? So this is still open question. We still don't know whether the CSH from the pozzolanic reaction or CSH from cement hydration is the same or not. We don't know. But it has similar characteristics. So this is very slow reaction. And why we can reduce porosity. Because we can increase this calcium silicate hydrate, right? First, we can expect there is more in the final stage, we can expect there is more calcium silicate hydrate, right? Calcium silicate hydration formation needs volume, needs empty space. So if there's more formation, generation of calcium silicate hydrate, then we can expect it has less porosity. Number two is it consumes calcium hydroxide. Because calcium hydroxide has main role of this calcium hydroxide is to maintain the high pH of the porous solution. It does not provide strength, for example. It does not have much impact on the volumetric contribution to the composite. So by changing this calcium hydroxide to the calcium silicate hydrate, so this is the main chemical pathway, right? CH from CSH. So we can also reduce the porosity. And lastly, the time difference. Time, because this reaction is very slow, okay? So what does that mean is this hydration, pozzolanic reaction is very slow, but effect of this pozzolanic reaction on material property is very high. It's very good, because when this pozzolanic reaction occurs, this cement hydration has been already started, right? Has been already occurred. Because OPC hydration starts kind of immediately at the beginning, but pozzolanic reaction needs time because it does not begin at the beginning. It needs hydration product, without this calcium hydroxide production from OPC hydration, this reaction will not occur, right? So this reaction needs time, and this time requirement is actually very beneficial in terms of to reduce the porosity, because when this pozzolani reaction is active, the structure has already some strength, right? So it has small pores, regular pores, and then this pozzolani reaction is very efficient to fill the remaining pores in the concrete. So you can expect if the cement hydration and pozzolani reaction, two different reactions occur simultaneously, then the pore structure is supposed to be high. But if OPC hydration occurs first, and then pozzolani reaction added later, and this addition, time-delayed addition, is very efficient.